Inside silicon, the technology behind everything. Powered by Semiconductor.
You know, for about 50 years, the entire tech world has danced to the rhythm of one simple idea: Moore's Law. The rule was easy: make the transistors smaller, and in turn, our chips get faster, cheaper, and way more powerful. But that incredible 50-year party, well, it's starting to face some serious headwinds. Something fundamental is changing in the world of silicon.
So that leads us to the billion-dollar question that engineers everywhere are scrambling to answer. If we're hitting the physical limits of shrinking transistors, then what's next? Is there another path forward to keep the engine of technology humming along? All right, let's really get into it.
For decades, it was almost like magic, wasn't it? Every couple of years, you could just count on it. The number of transistors on a chip would double, and our devices would get exponentially better. But that steady, predictable march of progress is running headfirst into some very real and very hard physical limits.
We're basically hitting three massive walls all at the same time. First up is the physical wall. At the 3-nanometer node, we're building transistors that are just a few dozen atoms across. At that scale, physics gets weird. We get things like quantum tunneling, where electrons literally start leaking through solid walls like little ghosts. That wastes a ton of power. Then there's the economic wall, and this one is just mind-boggling.
Look at that number, $20 billion. That's what it costs to build just one single cutting-edge chip factory. The barrier to entry is just astronomical. And finally, there's a third wall, a manufacturing one that most people don't even know about, but for our conversation today, it might just be the most important one. And this is it, the reticle limit. The easiest way to think about it is like this. The machine that prints the chip designs onto silicon has a maximum canvas size. You literally cannot print a single chip, a monolithic one, that's bigger than about 850 square millimeters. So let's put it all together. If you can't really shrink the transistors much more, and you physically can't make the chip any bigger, how in the world do you make it more powerful?
Well, the answer that the entire industry is converging on is a really elegant one. It's to stop thinking about one single giant chip and to start thinking in a modular way. This is the chiplet solution.
I love this analogy because it makes so much sense. For years, designing a chip was like being a sculptor with a giant block of marble. It's one piece, and you have to carve it perfectly. One tiny crack, one little defect, and the whole expensive thing is ruined. The new way is to build that same statue out of perfectly formed Lego blocks. It's way more flexible, it's a lot less risky, and it opens up a world of new design possibilities.
So what exactly is a chiplet? Well, it's basically a small, specialized mini-chip. It's a functional block of silicon, what we call a die in the industry, that does one job and does it really well. It might be a cluster of CPU cores, or a graphics engine, or maybe the I/O controller. The key is that it's designed from the ground up to be a team player, to be connected to other chiplets.
And the logic here is just so powerful. You take your massive design and you break it apart into these smaller, more manageable chiplets. Right away, your manufacturing success rate, what we call yield, goes way, way up. Because a tiny flaw only ruins a tiny, cheap chiplet, not the whole thing. But here's the real genius. You can mix and match manufacturing processes. You can build your high-performance cores on the latest, most expensive technology, but build your less critical parts on an older, cheaper process. You put the money where it really counts. Then, you just use advanced packaging to stitch them all together so they act like one cohesive, super powerful chip.
Now, this isn't just some cool idea on a whiteboard. This technology is real, it's here now, and it's powering some of the most advanced processors you can buy today. So let's take a look at some actual examples out in the wild.
And yeah, the biggest names in the business are all in. AMD was a real trailblazer here with their Zen architecture. They connected their CPU chiplets to a central I/O die using a high-speed interconnect they call Infinity Fabric. This is the design that powers their massively successful EPYC server chips. And Intel, they're using technologies like Foveros and EMI to build their latest CPUs, like Meteor Lake, from multiple little tiles. And get this, some of those tiles are made by Intel, and some are even made by their rival TSMC, all working together in a single package. It's a totally new way of building things.
This brings us to the real magic trick behind this whole revolution. I mean, if you've got these separate pieces of silicon, how on earth do you connect them so they can talk to each other so fast that the system doesn't even know they're not one big chip?
The answer is advanced packaging. And believe me, these technologies are just as complex and incredible as the chips themselves. We're talking about things like 2.5D interposers, which act like a tiny, super high-speed circuit board that the chiplets sit on. Or we can do true 3D stacking, where we literally place chiplets right on top of each other for the shortest, fastest connection possible. These techniques give us an insane amount of bandwidth between the chiplets, on the order of terabytes per second.
So this is the crucial point, the main takeaway. For the future of computing performance, the innovation in how we connect and package these chips is becoming just as critical, maybe even more critical, than just shrinking the transistors inside them. This is a huge shift in the industry's focus.
And of course, to make a true Lego ecosystem work, you need to make sure everyone's bricks can snap together. You need a standard. That standard is called UCIe. Just think of it like USB, but for chiplets. It's a common language that will eventually allow a designer to take a CPU chiplet from one company, an AI accelerator from another, and memory from a third, and just know that they'll all be able to talk to each other inside the same package.
All right, so this brings us right back to our original question. With all this incredible innovation happening, does that mean chiplets are the only way forward? Is this the silver bullet that saves Moore's Law? The answer, as you can probably guess, is a little more nuanced. Chiplets are a massive, absolutely essential piece of the puzzle. They solve those killer problems like manufacturing yield and the reticle limit, but they aren't the whole story. The future performance is going to come from a combination of all of these things. We'll still push transistor scaling where it makes economic sense, but we'll combine it with smart chiplet designs, even crazier packaging technologies, more 3D integration, and even exploring brand new materials.
And this quote just sums up the whole transition perfectly. We are fundamentally moving from an era that was defined by physics, how small can you make something, to an era that will be defined by architecture and intelligent design. It's not just about how good your single block of silicon is, but about how cleverly you can assemble all the different Lego bricks.
This transformation is happening right now as we speak, and it leaves us with one final fascinating question to think about. What becomes possible when chips stop being these secret, self-contained projects built by one company and instead become open ecosystems of interchangeable parts? What new kinds of computing will we invent then?
Inside silicon, the technology behind everything. Powered by Semiconductor.